Hello, ladies and gentlemen, and welcome to another episode of Chemistry Concepts. Trying something a little new today. We're going to go ahead and do some PowerPoint notes before I do my sample problems. By popular demand and several people asking, I've decided to go ahead and do um, some PowerPoint slides because some people said that they were helpful during class time. So I'm going to do a short PowerPoint video before I go ahead and show you guys kind of the sample problems. There'll be separate videos so you can decide whether you want to go ahead and go through the whole PowerPoint or whether you want to go ahead and go through just the sample problems. Today's lesson is going to be on what we call freezing point depression and boiling point elevation, which I have down here. It's one of the colligative properties of solutions. So right now we're talking about solutions in chapter 15. And before we go into what is boiling point elevation and freezing point depression, they are colligative properties. So let's go ahead and get a definition of what is a colligative property to begin with. And so as you can see here, we have definitions of what colligative properties are. Colligative properties of solutions are properties that depend upon the concentration of solute molecules or ions, but not upon the identity of the solute, which means if you make a solution, it doesn't matter whether you're mixing in, let's say your solute is sodium chloride, salt, or potassium nitrate, or uh, glucose or alcohol, whatever the solute is, it's gonna have the same effect on the solution, regardless of what it is. Now, how much of an effect might be different depending on the substance, because what's important is the amount. But what the identity of the solid is really has nothing to do with the property. It's the fact that something is being dissolved inside of something else. And the second bullet point here says that colligative properties include vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. I'm going to let you guys read on vapor pressure lowering. We really didn't cover a lot of vapor pressure when we talked about properties of liquids. So I'm not going to go into a lot of detail. Basically, it's whatever the vapor pressure of a substance, like water has a certain vapor pressure above it. When you start mixing stuff in there, the vapor pressure drops a little. And osmotic pressure is something else that you kind of have to go over, and we're not going to spend the time to go over what osmotic pressure is, but those are the four main colligative properties. The more solute you dissolve into your solution, then the more of effect on these things. Okay, so let's get to what is this boiling point elevation, freezing point depression stuff going on here. So let's go check this out. Okay. You'll recall that there's this thing called the phase diagram, and in this phase diagram, it shows you, it's basically a graph that shows you at what temperature and pressure a substance is a solid, a liquid, or a gas/vapor. Right? And we can figure out the normal boiling point and the normal freezing point of a substance just by going at 1 atmosphere, because normal freezing points and boiling points are what happens at normal atmospheric conditions. So at 1 atmosphere, if you follow the line across until it hits the line that shows the equilibrium point between solids and liquids, in other words, where freezing occurs, and then you go ahead and read it down, that'll give you the temperature on here, will give you the freezing point of the substance. If you continue across this line until you get to the other line between the liquid and the vapor, that is where you find, that is how you find your boiling point, right? Because once again, boiling is going a liquid going into vapor. So if you hit that line and you read down, you get your boiling point. Okay, and so we learned that back a few chapters ago in chapter 13. Now, once you start putting a solute inside of a solvent, right? And so this right here, this whole information is about the solvent. Once you start putting something inside that solvent, this is what happens. The green line right here is the original line. Okay, so it shows you the pure solvent and what the solid liquid equilibrium line looked like, what the gas liquid equilibrium line looks like. When you start adding solute, then there is this movement of this line, which is represented by green lines, off away from the middle and down. Okay. So you end up with this new line. Okay. So we went from having the vapor, this line represents vapor pressure of pure solvent. When you add solute to the solvent, then the solution has a new line, okay, and it gets pushed away toward where the purple line is right here. Same thing on this side, it gets pushed here toward the left. Right? So basically it kind of comes down. And now your solution is going to have a different line. So the purple lines represent what the solution properties look like. The green lines represent what that solvent by itself, without any solute in there, looks like. And you will notice that what happens here is, as this line here, the liquid solid line, moves toward the left, now the point where the 1 atmosphere line encounters that new line right here of the solid liquid equilibrium is much further to the left. It hits it earlier. And if you read down, you're going to end up with a new freezing point. Okay. And we represent the freezing point with this letter, letters right here. Capital T subscript F. T for temperature, F for freezing. So really, T subscript F is the freezing temperature. And it used to be at a certain point here. Right? The pure solvent line would cross the 1 atmosphere line over here, and this used to be the original freezing point. But as this line moved to the left, now it crosses earlier, and so now we see a different freezing point. The difference between the two is the freezing point depression. And we use the term freezing point depression because it's going to be lower. It's going to be further to the left, and the temperature scale here starts at the 0 all the way at the end. And so, you know, as you go further to the left, you're going closer to 0, so you're getting smaller, right? So we use the symbol delta to represent change. Delta is very commonly used to represent change in science and chemistry. So delta TF means the change in the freezing temperature. In much the same way, there's a similar effect to the boiling point. Right? As this line moves to the right here, now instead of hitting the the solid liquid line here for the pure solvent and looking up the boiling temperature, and you can see we use capital T lowercase b to represent boiling temperature, right, or boiling point. Okay. So T subscript F is freezing temperature. T subscript B is boiling temperature. But as our line moves to the right, now it's the purple line that is the line for the solution once we've added solute to solvent. And so we don't hit that line, once again, following the 1 atmosphere dotted line here. We don't hit that line till further to the right. And when we read down, we find a new boiling point. And that new boiling point, point 3 right here, is going to be further to the right. So we've actually raised our boiling point. Okay, so we have a increased boiling point. And so we represent boiling point, this boiling point change, as delta T subscript B. Once again, the T subscript B represents the boiling point, or the boiling temperature. And the delta represents the change, because we started off here, and by adding solute, that boiling temperature changed, and now it's over here. Okay. So that's why there is a boiling point elevation, and it always goes up. So we always say it's the boiling point elevation. There's also always a freezing point depression. That's why we're talking about boiling point elevations and freezing point depressions. And when we do the problems, we're going to use this equation. And what I did here in this equation is I circled each variable because people get all confused. There's like delta in it, there's different letters, some subscripted, some not. So it gets a little confusing. Okay, so what we got here is delta TF is the freezing point depression. How much is your freezing point going to drop? You know, you also have to kind of take into account what the freezing point of the substance is, of the solvent basically. Most of the information here is of the solvent. And how much the freezing point of the solvent is going to drop is what we're trying to calculate here. So delta TF is how much does the freezing point drop, and that's going to equal to capital K subscript F, which is what we call the molal freezing depression constant, which I'll show you down here at the bottom in just a little bit, times M for molality. All right, so normally there should be a little bit more of a tail on here, but Microsoft Word didn't have the little tail, so I just used lowercase m. Right? So in order to figure out how much the freezing point drops, you have to take the molality of the solution and multiply it by this thing called the molal freezing point depression constant. And every different substance, every different solvent, I should say, has a different KF. And down here, I have a table which is found in your book also. It's table 15.5 in your book that has 5 different solvents. And this is just a limited table. There are many more solvents, but just to give you an idea. And this table has the identity of the solvent, the freezing point, so you know what temperature that you could expect this thing to freeze at, and then the KF. This KF here, this last column, is the number that you use in your calculation. And once again, remember that this is for the solvent in the solution, not the solute. So you're going to get the KF for the solvent, you're going to multiply it by the molality, and that's going to give you your freezing point depression. Okay, pretty simple equation to use. It's just a matter of finding out what everything is at, and knowing what is one variable, because one of these variables has 3 letters in it, including a Greek one. The other variable has 2 letters in it, and the third variable only has 1. But we know that that third variable, molality, actually has an equation to it. Molality is equal to moles of solute over kilograms of solvent. So you might have to calculate it out, and you're going to need to know the formula for that. Okay. The last slide I'm going to show you guys is that for boiling point elevation. And one thing you're going to notice is that it's basically the same equation. It's just for boiling points as opposed to freezing points. All right, so for this one, once again, delta TB, delta T subscript B, is the freezing point, the boiling point elevation. How much the boiling point is going to change. If I have water, its boiling point is 100 degrees Celsius. So if I have pure water, I should have a boiling point of 100 degrees Celsius. But once I start putting something in water, whether it be sugar, whether it be potassium nitrate, whether it be copper sulfate, whether it be salt, then that boiling point is going to start rising. How much does it rise? Well, it depends on this thing called a KB. And down here below, we have a table with KBs here. And then you take that number and you multiply it by the molality. Okay, so notice how it's the molality that we use in this equation in order to get us our boiling point elevation and freezing point depressions. And once again, this table down here, same 5 solvents. That gives you their boiling points. So benzene, let's see the previous slide, benzene, had a freezing point of 5.5 degrees Celsius, and here it has a boiling point of 80.1 degrees Celsius. And then there is the KB. Okay, and the units for these guys are degrees Celsius per molal, because if you take the degrees Celsius, take the KB at degrees Celsius per molal, you multiply it by molality, or molal, the units are molal. The molal is going to cancel, giving you degrees Celsius as your answer. Okay, so it's these guys that you plug in. You do not plug in the boiling point. What you might do at the end of the problem is either give a boiling point depression or freezing point, boiling point elevation or freezing point depression. But if they ask you for the specific boiling point, then you just have to add the boiling point elevation to this boiling point. Right? So if there was a boiling point elevation of 5 degrees, then the solvent was water. Well, water's supposed to boil at 100 degrees. If the boiling point elevation was 5 degrees, that means it just elevated by 5. So you take the 100 degrees, add 5, and that's going to give you your new boiling point, 105 degrees. Okay, so I hope this was clear. I hope it was helpful. My next video, we're going to do some problems on calculating this using these equations. And then we'll do a problem that'll show us how we can, by making a solution, we can figure out the molar mass of an unknown substance. Okay.